This is a walkthrough of problem 3 on practice exam 2 of module 1 in the book Problem Solving Guide for Mechanics and Thermodynamics. Train starts from rest, accelerates at a constant rate of 1 meter per second each second for 30 seconds. After the acceleration period, it stays at a constant speed for 3 minutes. Then it decelerates uniformly to a stop at the next station over 10 seconds. What is the average speed of the train for the journey between stops? What is the distance between stops? On neat, well-labeled graphs, plot the acceleration of the train as a function of time, the velocity of the train as a function of time, and the distance traveled by the train as a function of time. This is going to take some time. Let's not be in a hurry. Start with a good diagram and really think about what's going on and understand what's going on. So there's my train and my train tracks. The train is at the first stop. It's going to travel to the second stop. It's going to accelerate, then it's going to coast, then it's going to slow down. The total time for the trip is actually given. The acceleration, it says, is 30 seconds. The coast is 3 minutes. The deceleration, the stopping, is 10 seconds. So we can add those up. 3 minutes, 40 seconds. 220 seconds. Total time between stops for the train. And we can put those phases on the diagram. 3 phases of the trip. The acceleration phase, 30 seconds long. The coast phase is 3 minutes long, and the stop phase is only 10 seconds long. The speed of the train at the end of the acceleration period must be 30 meters per second. Starts from rest, changes by 1 meter per second every second for 30 seconds. It's going to end up at a speed of 30 meters per second. You can use an equation if you want, but thinking about it is better. Its speed during the coast must be 30 meters per second. The speed at the end of the journey must be 0. So during the acceleration phase, 0 to 30 at a constant speed of 30, then a stop in 10 seconds. To get the average speed of the train over the entire journey, which is part A, we have one move. We have to get the total distance traveled and divide it by the total time taken. That's the definition of average speed. During the acceleration phase, it goes from 0 to 30. The average speed is 15 meters per second during the acceleration phase, and it averages 15 meters per second for 30 seconds. The distance traveled during the acceleration phase is the average speed times the time, which is 15 meters per second times 30 seconds, 450 meters. During the coast phase, the average speed is, now don't screw this up. Students screw this up all the time. What's the average speed during the coast phase? If you try to use an equation and do initial speed and final speed, if you do it right, you're not going to have a problem. But if you do it wrong, there's an opportunity to do it wrong if you use an equation. But if you think about it, it's going 30 meters per second the entire time. The average speed is 30 meters per second. During the coast, the speed's not changing. If it averages 30 meters per second for 3 minutes, it travels the distance of 5,400 meters, 5.4 kilometers. During the stop, it goes from 30 to 0. The average of 30 and 0 is 15 meters per second, and it averages 15 meters per second for 10 seconds, so the distance it travels is 150 meters. The total distance is the distance for the acceleration, the distance for the coast, the distance for the stop. If we add all those up, we get 6,000 meters, which is actually the answer to part B. For the entire trip, the average speed is 6,000 divided by 220. Total distance divided by total time, 27.3 meters per second, and we're happy with that number. Most of the time it's going 30, but there's an acceleration and a deceleration phase in which it's going slower than 30, so we should expect the average speed to be a little bit less than 30. Nice and reasonable. If we got a number bigger than 30, we would know it's wrong. Now we have to do the plots. Acceleration is relatively straightforward. It's given that the acceleration is 1 meter per second squared over the first 30 seconds in the acceleration phase. During the coast, it's 0. During the deceleration phase, it goes from 30 to 0 in 10 seconds. If it goes from 30 to 0 in 10 seconds, it's changing by minus 3 meters per second each second. So it's plus 1 over the first 30 seconds, 0 for the coast, minus 3 during the break. There it is. Plus 1, then it drops to 0. That's the coast. It's not accelerating. And then it's minus 3 from 210 to 220 seconds, the braking phase. Now the speed goes linearly from 0 to 30 meters per second in 30 seconds, stays at 30 meters per second from t equals 30 seconds to t equals 210 seconds, 3 minutes, then drops linearly to 0 in the 10 seconds from 210 to 220 seconds. Here it is. 0 to 30 meters per second smoothly in 30 seconds. Coast, then a quick break from 30 to 0 in only 10 seconds. Now we have the distance during the acceleration. Acceleration is 1 FAT squared, the initial speed 0. So that is the shape of the line. It's a parabola during the acceleration phase. During the coast, it's a straight line. The slope is 30 meters per second. During the coast, the distance traveled increases at 30 meters every second. During the deceleration, we have an initial speed starts at 30. The acceleration is minus 3 meters per second squared. T is the time during the deceleration. So the plot looks like this. The acceleration phase from 0 to 30. That's a curved line from 0 to 30. The slope is 0 at the beginning because the speed is 0. Then there's this long straight line. And then from 210 seconds to 220 seconds, it curves downward, concave downward, and stops at 220 seconds. So that's the problem. But let me ask you these questions. What is the slope of the line at 20 seconds? Right there. What's the slope of the line right here? What's the slope of the line at 214 seconds, which is right there? Well, the slope of the line is just the speed. So after 20 seconds, the train is going 20 meters per second. After 214 seconds, let's see, it's going 30 at 210, and it slows down 3 meters per second each second. After 4 seconds, it's going to get reduced by 12 meters per second from 30. So at 214 seconds, the slope of that line is 18 meters per second. That's problem 3.